and we can end the class at around like 2:30 or 2:35. My name is Juan Huang. Juan, so pronouncing Chinese is Juan, not in Spanish. So this lecture, I'm going to talk about cochlear implant and hearing loss. So these are the references that you should check, you should read. Some of the slides I used, I copied from Dr. Eric Young's lecture for last year. He retired last year, so that's why I'm here. Yeah. Just for this lecture. Dr. Young also do the SBE2 lab, and I'm also will do the lab with you guys next month. So what is cochlear implant? Have you ever heard about cochlear implant before? Do you know? Oh, okay, so some of you know. This is the most successful neuroprosthesis in the, so clinically used, very popular, started from 1980s. The first several years, cochlear implant was just used for restore some coarse hearing. For example, for the severe deaf people, as long as you can get some cue of, oh, there's something happening there, there's sound from there, that's fine. That's first decades maybe, and then started from actually 1990s when the cochlear implant process, speech processor strategy had made big progress. Then cochlear implant has been used as a very successful clinical treatment for hearing loss. So cochlear implant is a surgically implanted electrical device that can provide a sense of sound to people that with profound hearing loss. I will show you the audiogram of deaf people with what kind of audiogram that the patient has to get a cochlear implant. Even a hearing aid doesn't work. So you will see that in a minute. Do you know Alessandro Volta? Any clue of him? He's the inventor of electrical battery, and he's an Italian physicist. And yeah, so he's a pioneer of electricity and power. Probably he is the very first person who did the study using electrical stimulation to generate some sound, generate audition. That was in 1980s. So since he discovered the electrolytic cell, so he once tried, he just by curious, he wanted to see how electrical stimulation would work to his brain. So he inserted two metal rods insert into his ear. The power was quite large, like 50 volta back then. And then he just heard boom. And he reported, he actually wrote a paper about that simple experiment. He reported that, oh, I heard something like bubbling sound, like boiling a boil of water, soup. So that finding stimulating or inspired a lot of people who were trying to develop some treatment for hearing loss back then. So after his simple experiment, in the next 50 years, people have been trying to do similar experiment, try to develop some device using electrical stimulation to restore hearing, but failed. Back then, the sensation of the patients mostly described as momentarily. It's just momentarily. It just happened once and then stopped, or there's no tonal quality. It's just noise, nothing else. It doesn't help much. A current cochlear implant system that has been used very as a popular hearing loss treatment nowadays. These are the components of current cochlear implant. So you have a microphone here. Microphone pick up the sound from the environment. And then the headpiece connected with it's a magnetic headpiece connected with implantable cochlear stimulator. This is stimulator. And there is a coil, cable to speech processor. This picture actually shows a previous version, old version of cochlear implant. The speech processor connected with the headpiece through a cable, and then a pretty big, like small computer, usually carried like somewhere as a backpack or put in a pocket. But nowadays, a newer version, the cochlear implant. So the newer version cochlear implant, you have the magnetic headpiece, and then the processor is tiny. It's just this big. And then this part, for cochlear implant company, they try to develop different settings for different environment. For example, in quiet condition, in a noisy environment, listen to speech or listen to music. So you can turn, there are different modes, options there. The speech processor just like this much. So it's very, very portable device. If you ever get a chance, you can try to look, well, you can actually watch a cochlear implant surgery on YouTube. A lot of doctors posted video on YouTube. I observed a cochlear implant surgery like probably 4 years ago. Dr. Charles Lim, he was a doctor at the laryngology department, but he just moved to UC San Francisco. It took him about like 20 minutes, less than 20 minutes, to do the whole surgery. So it's a very standardized surgery. And did Dr. Huang give the lecture of hearing auditory pathway? Not yet. Okay, so I'm going to go over the steps in cochlear transduction so that you get an idea of why a cochlear implant, electrical stimulation device would work, would generate audition. So this is a simplified auditory pathway, peripheral pathway. So this is the air pressure, your pinna or your ear canal connected, collected some air vibration force, like transmit into through the tympanum, through the middle ear motion to the inner ear. This part is the inner ear. So from here, the sound is acoustic energy vibration in the ear, and then through the middle ear, the three tiny bones, the acoustic energy converted to mechanical energy, mechanical vibration, and then the mechanical vibration being activated and also amplified through the middle ear structure and then activating the liquid inside the cochlear. In the cochlear, still at first, still the mechanical vibration activating the liquid inside the cochlear, and then the mechanical vibration activating the basal membrane. Basal membrane, this is a basal membrane, the basal part connected with the middle ear. It's respond to high frequency, and the apic part respond to low frequency. And with the basal membrane vibrating, these are the organ of Corti. This is one example of inner hair cells. The hair is vibrating like to one cycle. So when the basal membrane vibrating upward, it changes the direction of the hairs on the inner hair cell, and then the inner hair cell somehow converted. There's a mechanism, Dr. Huang will tell you more, converted the mechanical energy into neural pulses. So at this point, within the cochlear, inner hair cells converted the mechanical vibration into neural energy, neural pulses, and then projected to up auditory pathway. So a working procedure of cochlear implant, like these are the steps to convert the whole steps of a normal cochlear transduction procedure. These are how a cochlear implant would work. Microphone pick up the sound, and then auditory signal being processed by the speech processor and extracted or analyzed, extract some of the component of the acoustic signal, and then send it to the electrical stimulator, generating the electrical stimulator, generating some pulse strings, send it directed to the receiver, and the receiver send the electrical stimulation to, let me see. Here, directly send it to the electrode. These are the cochlear implant electrode array inserted into the inner ear. These are the cochlear. It's like a nail shape structure in your inner ear. The electrode array inserted into the cochlear. As I just said, the steps of the cochlear transduction is, this is the basal part, this is the apical part. So the apical part respond to low frequency information, the basal part respond to high frequency information. You can see this electrode array could not reach the apic part at all. So just here, because of the limit of the material of the electrode array, and also because of the surgical itself. And so this tiny dots or electrode, electrical pulses sent through this electrode and directly activating auditory nerve fiber. Instead of stimulating the inner hair cells to generate neural pulses, this electrode directly activating auditory nerve, and auditory nerve being activated generate action potential and send it to the up layer of the auditory pathway, so that audition being generated and stored. So the main point of cochlear implant, why does a cochlear implant work, is cochlear implant bypassed the peripheral cochlear mechanisms. The important function of the cochlear is converting a mechanical vibration into neural pulses. A cochlear implant using electrical stimulation directly activating or stimulating the auditory nerve to convert acoustic energy into a neural energy, neural pulses in the auditory nerve, and then send it upward. Like above the auditory nerve, everything else is the same. Not exactly the same, but the energy, how does energy being transformed and being interpreted as a sound is similar. So this is the audiogram of potential CI users. If a person go to doctor complain about his hearing, the first thing the doctor would check is this person's hearing. We have a very good audiometer in our lab at Cochlear 106. If you're skeptical about your hearing, you can go to Cochlear 106, make an appointment with me, and then we can do the audiogram for you. So x-axis is the frequency, y-axis is the hearing level or hearing threshold. Usually the whole testing started from presenting a 1K sound to you. And by adjusting the intensity of the sound based on your response, we will get your threshold of at a certain frequency. In this case, this patient, for 250 hertz tone, it needs at least 85 dB sound to be heard by this person. So this is very abnormal. It's profound deaf, you can say. Like 110 dB for 2K, 4K, and 8K. That means in a natural environment, in a normal environment, this person cannot hear anything. For a normal audiogram, it should be like this. For you guys, you're so young, so your curve should be like this. Around 0, 10 dB. Yeah. Across all the frequencies. And also your left ear and the right ear should be balanced. The threshold between your two ears for a certain frequency should be less than 15 dB. Yeah, that's supposed to be normal hearing. But for patients with this audiogram, there's no way to like using a simple amplifier to restore his hearing. Has to be cochlear implant. So this is the basic unit of hearing unit in the cochlear. This is the organ of Corti. The green cells are inner hair cells. The orange cell is outer hair cells. This is the basal membrane. And the basal membrane, remember, the shape of the basal membrane is like a snail shape. So electrode array inserted into here. And this unit, so the outer hair cell usually its function is amplify the basal membrane displacement or amplify the mechanical vibration. And the inner hair cells, the function is a transducer for auditory nerve fibers, meaning it converts mechanical vibration into neural pulses. That's a normal natural hearing unit in your cochlear. But for those people with profound deaf, this is the So if this is a normal cochlear, this is after death. You can see what's the difference here. So these are a normal cochlear, normal basal membrane. So these are the outer hair cell, inner hair cells. Looks very neat, lined up nicely. And this is a slide with after damage, the inner hair cells. You can see here, this is missing inner hair cells, nothing here. These are damaged hair cells, so these hair cells does not line up nicely. And these are normal inner hair cells. You can see like the fan-shaped inner hair cells looks very nice. And these outer hair cells, again, you can see damaged outer hair cells here. Normal hair cells here, usually V-shape or double shape, and missing, these are missing hair cells here. So with missing outer hair cells, at least that part of basal membrane lose the function of the vibration of that part of basal membrane won't be amplified enough to generate a strong vibration, and then to make the inner hair cells convert the mechanical vibration into neural pulses. Not to mention there are a lot of inner hair cells also missed here. So this is a big problem. You have to find a device. A cochlear implant device is the device that bypasses the whole procedure. Can you think about why a cochlear implant could bypass this part? There's a pre-circumstances there so that cochlear implant electrode can do its work. Can you think of anything as, for example, a patient question? So a patient who has a damage in his inner ear, who also has damage in his auditory nerve, would the cochlear implant work? Yeah, it won't work. Because the cochlear implant electrical array only replaces the function of this part. It won't replace the function of the auditory nerve. So, very fortunate for those deaf people, the auditory nerve fibers often survive the loss of hair cells. Usually 10 to 70% would be still there. So you can see here, this is a 93-year-old man with a considerable hair cell loss. You can see from this slide, so here are some hair cells, you can see, but this part of hair cells all lost. So nothing here, no hair cells, but remaining fibers. So these are the fibers still there. So 93-year-old man in hair cells. So that's why you can use electrode to directly stimulating this remained auditory nerve fibers. Yeah. And one thing you might have observed that for this 93-year-old person, the inner hair cells lost were all high frequency part, and low frequency part has reasonable inner hair cells, like still here. Yeah. So usually for a senior person, not that senior, for persons like in his middle age, he started to lose his high frequency hearing. That's very normal. Yeah. This is a schematic figure showing the connection between cochlear and auditory nerve. So the cochlear auditory nerves here. So these are the ganglion cells. These are the fibers. Fibers connected, or auditory nerve connected with inner hair cells and outer hair cells. A damaged inner ear is like this. So the loss of hair cells results in efficient processing of auditory signal, and a cochlear implant directly stimulate auditory nerve, like direct this part of the auditory nerve, and then the spinal ganglion cells generating neural pulses send it to the up layer of the auditory path. Now, you know the mechanisms of how a cochlear implant works, but what are the main practical technical challenge for designing a cochlear implant? So you can see this is the electrode inserted into the inner ear cochlear. As I just said, this coil, this electrode array can only reach at this part. So this part, even there's still a lot of auditory nerve there, but cannot be stimulated because this electrode array can only insert up to here. And these orange ellipses are the location of spinal ganglion cells. And you can see these are the electrode, the location of the electrode, one electrode, two electrode. So electrode send out the electrical pulses. It has to be strong enough to activating the ganglion cells here, located here. And also there's a problem. So for electrical stimulation, send it from, for example, from this electrode, it's strong enough, intensity is high enough to activate in this ganglion cells. But electrical pulses sent from this electrode could be also strong enough to activate in this ganglion cells. So the citation pattern being overlapped, that causes problem. So two problems. One is how to avoid the damage in the remaining cochlea when a doctor insert the electrode array into the nail-shaped cochlea. Although these electrode array are like the material is soft enough, but it cannot be too soft. Otherwise, it cannot be like coiled into this turns. Just one turn stop here if it's too soft. So it has to hard enough to be inserted along this this tube, along the cochlea, along the basal membrane. That's one problem. Another problem is how to stimulate in fibers in the apex. So there's no way you can do that. That's for surgery, the problem. And that these two problems are what you have to think about when you design a cochlear implant. Especially the electrode. That's the most difficult part. So why does a cochlear implant, why does that electrode array can work or can store normal hearing, especially for speech communication? So the most successful part is because the tonotopic organization of the basal membrane, as I said, high frequency here, low frequency here, middle frequency here. So that electrode array inserted electrode at the basal part, activating the high frequency part, and apex part activating the low frequency part. And then here's a demo showing you the tonotopic organization, so that you get idea. It's very slow. Oh, so this is middle frequency, high frequency. So different frequency component activating different part of basal membrane. Low frequency here, high frequency here. Very low frequency here, high frequency. So you get idea of how, when a natural sound, when music played, how does your cochlear work? As long as the electrode array as long as the cochlear implant can processing the natural sound, decompose that natural sound, complex sound, into different frequency components, and also extract the critical information of that part of frequency and then send it to the electrode, activating different part of the auditory nerve that connected with a different part of the basal membrane. It should work. So that's a very simple logic, and engineers try their best to make it happen. Okay, these two problems. This for designing a cochlear implant. The problems: electrode here, it can't reach the basal part, and the excitation pattern along the basal membrane overlapped. So you can imagine for that demo, if electrode activating the basal part also activating the apical part of the basal membrane, the auditory nerve, it will ruin out the whole auditory processing. So it shouldn't. So the restoring of the hearing is impossible. So this is the spectrum of a natural sound, a natural speech sound. You can see if you record acoustic signal and do FFT, decompose that acoustic signal into frequency domain and time domain, and you will see this. This is a 600 millisecond sound syllable, and y-axis is frequency. Let's hear the sound. Okay, it's too short. Basketball. So by analyzing this sound spectra, this is spectral plot of that sound. And you can see there are low frequency component here. This very low frequency around 100 hertz, 200 hertz, 400 hertz, and that this curve showing the contour of the energy, the first formant, and this contour showing the next formant or energy. So this actually showing the energy distribution of this whole sound. So for designing a cochlear implant, how to programming, how to code this critical information for this particular sound is very important. Like for understanding basketball here, by looking at the spectrum plot, you probably think, okay, if I'm an engineer, I have to figure out a way to code this low frequency for sure, because without this part of low frequency information, I don't know whether the person talked to me is male or female voice. This part of frequency gives you the cue of speaker identity. And the energy distribution along the frequency domain actually code, for example, for a simple vowel, the formant 1, formant 2, the ratio between the formant actually code what exactly the vowel is perceived as. R and M might be different. The first formant might be the same, and the second formant would be at a different frequency. So these are crucial cues that attribute to your perception of speech. So this is the second. As an engineer, when you design this processor, you have to think about, okay, I have to code this, I have to code that. And then in general, for speech perception, remember a cochlear implant designed for restore hearing, restore basic hearing function, speech communication. For speech, the whole range of speech, the most important frequency range is about 100 hertz to 5,000 hertz. There's some higher frequency energy, but if you just low pass filter out those high frequency energy is fine. Your speech perception will still be fine. So even a human ear, you have the hearing range from 20 hertz to 20K. For designing a cochlear implant, you just need to think about, okay, I'm just going to code the information between 100 hertz and 5K should be good enough for your speech perception. So this is what I just said. So this is a sentence, for example. If you zoom in this part, this could be word or part of the word, a vowel actually, and zooming and then analyzing the information. This is the frequency, and you will get the first formant here, second formant here, the third formant here. So these are crucial parts. So that's why the first, that's why the engineers, when they design a cochlear implant, they emphasize these information. So there's a strategy of speech processor. They code voicing detector. That's fine. So F0 estimator. So they code this part. So to code the male female voice, and then first formant, second formant. Remember, so second formant, first formant, the only thing different. So x-axis is the same. Y-axis is just the frequency. So the frequency are different. So that this input signal decomposed into some of the low frequency, F0, F1 frequency, F2 frequency, and higher frequency. And these frequency bands are pretty coarse, up to 6K. And then this information be converted into electrical pulses, converted to electrical pulses. And these information that considered are not that crucial for vowel perception, just convert coarsely from acoustic to electrical stimulation, electrical pulses, and then send it out through the coil, send it out to the electrode. And I will show you in a minute what's the performance of patients by using this kind of speech strategy to code the acoustic information. That's one strategy. I'm going to skip this frequency compression because that's the strategy I just mentioned. Turns out the speech performance was not like good enough. So engineers have to think about other ways. So some other engineers think, okay, I'm going to forget about the formats, F1, F2, forget about it. I just divide all the frequency into like several bands and then compress. Remember, for a cochlear implant, there's only 24 electrodes and only 22 electrodes being used for electrical stimulation. The other two are references. So you have like 3,000 like audio fibers. So the channel, the frequency channel along your basal membrane is much, much larger, the number, than the electrode number. So the engineers think, okay, I'm going to divide this large frequency, compress into like a 22 channel, for example, or 8 channel, and then send the information to one electrode, see what happened. That's a compression strategy. And the third strategy that engineers thought about, for this strategy also, they get rid of the format idea. Just record the signal and then bandpass filter the whole acoustic signal, divide it into some from low frequency to high frequency. That's the first step. They do band filter, and then for each band, they extract, there's a rectification, low pass filter as well. They extract the envelope of this information. You can see, take this band for example, extract the envelope, get rid of the frequency variation here. Get rid of the detail of the frequency variation, just get the amplitude envelope, like band pass 1, the envelope, band pass 2, the envelope, and then so forth up to the high frequency. And then send this envelope information to the third stage. The third stage is actually compression, or just call it electrical pulses generator. It generates about 400 hertz electrical pulses, biphasic pulses, and before this part of information modify this electrical pulses. These are just uniform electrical pulses for 400 hertz. Like standardized, and then for each band pass, the extracted envelope being used to modify the electrical pulses, so that the electrical pulses get the envelope, get the energy variation, and change the pulses. The pulses, although these are 400 hertz pulses, but it adopted the envelope of this bandpass filter, the envelope of this got from this band pass filter. And then you got the variation of the envelope, and the frequency remains the same. So these are low frequency information. These are high frequency information, but the high frequency information, the high frequency, get rid of it. Just the envelope of the high frequency information remained to modify the electrical pulses. Okay, now send this modified or final electrical pulses, coded electrical pulses, to corresponding locations of the electrode. This is the basal part. This is the high frequency part. High frequency information, the envelope is like this. This electrical pulse, modified electrical pulses, is sent to this electrode. Middle frequency is sent to the middle electrode, and low frequency information sent to the apex electrode. Okay, that's the currently used strategy. Is called CIS, continuous interleaved sampling. Continuous interleaved sampling. What is interleaved? Interleaved means here, so for the electrical pulses, to avoid the overlap of the excitation pattern along the electrical array. So for any electrical pulses, there's no simultaneous electrical pulses across all the 22 electrodes. So for electrical pulses start from here at the same time, the first pulse of the channel 2, channel 3, channel 4 would be offset from each other, so that there's no, at one time, there's no two pulses being sent to the electrode. That avoid the interaction across all the electrodes. That's a very successful strategy. So these are the some of the experimental results using CA strategy. Y-axis is the percent correct of speech perception. And this is CIS strategy. You can see the same patients using two strategies. The speech performance increased by like almost all of the patients had better performance using the CIS strategy. And also, if you do the correlation analysis, you can see all the CA condition. At CA condition, all the speech performance would be like would be poorer than the CIS condition. So these are the strategies that when designing a cochlear implant, engineers have to think about. So there are surgical problems, there are cochlear implant designing, speech process designing problems. And so what does a cochlear implant sound like? Let me show you the demo. One channel. Four channels. How many channels do you need? Oh, this is music. It's horrible. This is 4-channel music. Okay, so now you know how bad cochlear implant users listen to music. So I once presented some of the demos to parents who has cochlear implant, like children. They a big part of them just burst into tears right at the moment when they hear the simulation, because they thought their kids, they can talk to their kids, they communicate with their kids. Given some training, their kids are pretty good, perform very good for speech, but not for music. Why? Okay, I'm going through quickly at this. Well, this is the strategy that being used to the speech processor. Remember, the idea, the goal of the cochlear implant is to store speech communication. So the strategy were designed for speech and not for music. That's why like take this for example. This is the original speech. This is the spectrum of the speech. You can see this frequency variation here. But when it is after processing, the spectrum plot looks like this. The variation of the pitch, the variation of the frequency all gone. So there's only envelope information remained. The fine structure or the frequency variation are lost. That's why you cannot hear pitch, because there's no pitch being like directly encoded in the strategy. Another problem, of course, the electrode cannot reach to the low frequency part, so you lost the most part of the low frequency information. Auditory nerve not activated, so there's no pitch. And this is a frequency map. So for cochlear implant, there are 22 electrodes. These are frequency map, but this is channel number. These are details, activate electrode. These are dynamic range. Dynamic range means the intensity range of the electrical pulses. For individual electrode, they're varied, so you have to adjust that. And also low frequency, high frequency, you can see this 21 electrode, for example, is so the 22, 188 hertz to 313 hertz, almost like 2-octave frequency range. How would you expect you can hear music with this coarse frequency code? That's impossible. But for speech, it's really good. That's why it is very successful. So this is the experiment. Okay, I'll stop here. So this is speech performance tested with CI users with some training. So y-axis is percent correct, x-axis is training, the experience of wearing a cochlear implant. You can see the first month, there a lot of patients' speech perception reached already like above 65%. Giving 2 years of training, almost like a majority of people can perceive in speech like as good as almost normal people. They can talk through the phone, but they had some problem with communicating in a noisy environment, because in a noisy environment, pitch is a very important cue for you to understand speech in a noisy environment. In quiet environment is not a problem at all. So there are some other things that will, you can download the slide from Blackboard to think about a lot of detailed things. Sorry, this class starts really late, and we don't have much time to go into details. If you have any questions, or if you are interested in testing your audiogram, just send me an email. We can make an appointment for that. Okay.